X-rays were discovered in 1895 when it was shown that cathode rays produced a type of radiation which caused certain substances to fluoresce. So here's our cathode ray tube, and this stream of negatively charged particles created a type of energy or electromagnetic radiation which became known as X-rays. And X-rays have wavelengths on the order of 1 angstrom unit, which is 10 to the negative 10th meters. Antoine Becquerel discovered that uranium emits radiation continuously. It's said to be radioactive. Now, Ernest Rutherford identified 2 types of radiation emitted from radioactive substances. He called these 2 types of radiation alpha particles and beta particles. Alpha particles are positive because they're helium atoms with 2 electrons removed, while beta particles are electrons, so they're negative. There's actually a 3rd type of radiation, which is called gamma rays. They do not consist of particles, have no charge, and they're unaffected by an electric field. So here's kind of what we have. If we have a radioactive substance, let's say we have uranium over here, it's going to emit 3 types of radiation: alpha, beta, gamma. So let's say I have charged plates. I have a negative plate, I have a positive plate, and we're collecting the radiation over here on the screen. Well, as uranium emits radiation, the alpha particles are going to be attracted to the negative plate, so your alpha particles would become up here. Your beta particles, which are negative, would be attracted to the positive plate, and then your gamma particles are unaffected by an electric field or a magnetic field, and so they travel straight through. So alpha, positive up here, gamma, no charge, go straight through. Beta, negative, would be attracted to the positive plate. And Rutherford discovered that when an element undergoes radioactive decay, when it emits these particles, it's converted into a different element. The nuclear atom. In 1909, Ernest Rutherford, together with some other scientists, carried out a series of experiments in which very thin foils of gold were bombarded with alpha particles emitted from a radioactive source. So we have an alpha particle emitter, a radioactive substance. So we're shooting positive particles, alpha particles, through gold foil, so through these gold foil atoms. And what he discovered was, in this experiment, is that most of the particles went straight through. So most of the alpha particles went straight through the gold foil. However, some of the alpha particles were deflected, and some were deflected at rather large angles. He was using Thomson's model, which was the plum pudding model, and he said that based on Thomson's model, where the electrons are stuck in place and the positive charge is spread throughout, that the alpha particles should pass through the weak electric field largely undeflected. Now, most did pass through the electric field undeflected. However, a few alpha particles were deflected through very large angles, and it was only like 1 in every 20,000. So a very small portion were actually deflected at these large angles. Rutherford's atomic model says that most of the mass and all of the positive charge is centered in a small region he called the nucleus. Most of the atom is empty space. So the nucleus holds your mass, which are your protons and your neutrons, and it's very small compared to the rest of the atom. And then there must be a certain number of electrons that are floating around the nucleus to account for the fact that atoms are neutral. So Rutherford, based on the gold foil experiment, came up with the idea of the nucleus and that most of the atom is empty space. Here's just another picture of the gold foil experiment. And you have your alpha particles. Most of the alpha particles went straight through. But every now and then, once those alpha particles, which are positive, hit the nucleus, that's where you get the deflection. Because if a positive alpha hits the positive nucleus, that's where the deflection would occur. The diameter of the nucleus is 10 to the negative 12 centimeters. The diameter of an atom is 10 to the negative 8th. The nucleus is very, very small compared to the rest of the atom. Scientific method. I'm not going to cover this. As long as you know what a hypothesis, a theory, and a law are, you will be good on the scientific method. Isotopes. 1912, J.J. Thomson determined the charge-to-mass ratios of positive ions produced in the canal ray tube. He found that these ions of pure neon had different charge-to-mass ratios. Well, if they have the same charge, he determined that they must have different masses. And he called atoms of the same element that have different masses isotopes. In 1913, Henry Moseley reported on experiments in which different elements were used as targets in an X-ray tube. And he showed that the frequencies of X-rays emitted from elements increased in a predictable way with an increase in the positive charge for the elements. Now, the number of protons in the nucleus of an atom is known as its atomic number, and I'll give it this symbol Z. In 1932, James Chadwick isolated a third type of particle, which he called the neutron, and the neutron was the last subatomic particle to be discovered. So here is a comparison of the three types of subatomic particles: proton, neutron, and electron. What I want you to notice, first of all, the masses. Protons and neutrons are essentially the same mass. Electrons are about 2,000 times smaller than a proton or a neutron. As far as charges, don't worry about the actual charges, but you'll notice a proton has a positive charge, whereas the electron is exactly the same charge but negative. We don't actually use the actual charges, we use relative charges. We say a proton is positive 1 and an electron is negative 1. The number of protons is equal to the number of electrons because atoms are neutral. Isotopes are atoms of the same element that contain a different number of neutrons. We'll give the mass number the symbol A, and that's the total number of neutrons and protons present in the nucleus of an element. The symbol AZX represents what we call a nuclide. So that nuclide will tell you the mass number, it will tell you the atomic number, it will tell you the chemical symbol. Also, if an atom loses or gains electrons, it becomes an ion, so sometimes these will have a charge associated with them as well. For example, with 2010 neon with a plus charge, the top number, that's the mass number on this nuclide. The bottom number is the atomic number in the nuclide. And since there's a positive charge here, that means it is an ion. So if I give you a nuclide, you need to be able to tell me the number of protons, electrons, and neutrons. For example, 3517Cl. Well, the bottom number is atomic, that's the number of protons. So I have 17 protons. The top number is the mass number, which is the number of protons and neutrons. So if I want to find neutrons, I simply have to subtract 35 minus 17. Since this has no charge, that means I have to have 17 electrons as well, because protons are positive, electrons are negative, and if they cancel each other out, that will give you no charge. In that next nuclide, 8035Br, there is a charge, but again, bottom number, number of protons, 35. Top number, protons plus neutrons. So if I subtract, I get the number of neutrons. This one has a charge. Protons are positive, electrons are negative, and so if there's a negative charge overall, that means there have to be, in this case, 36 electrons compared to 35 protons, which will leave you with a negative charge overall for this ion.